Hey, Liu. A little bit. And so I'll be showing basically a MATLAB code, and the code that I'm showing is uploaded on Canvas. But we're not gonna be developing anything in MATLAB. It's just a demonstration basically. Mhm.
you have class, honey?
I did see it. Yeah, it's exciting. I think it's a big step outside their comfort zone, but we'll see. The trailer was kind of jank. Like the Pokemon were like kind of like flickering and kind of like clipping into stuff. So hopefully they iron out the technical stuff. But the premise is really cool. Yeah, that makes sense. Mhm. Yeah, probably more powerful console would definitely help it. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? These lecture notes, yes. So we'll be starting lecture note 7, and there's a little bit of lecture note 6 that I want to go over again, just because I know last time everyone was kind of fixing their code at the end. Yeah, good. Yeah, I've heard it's a busy week, so I know a lot of midterms are landing on this week. Including one of my own that took place earlier today, and so oh shoot, next week is busier. Oh, my bad. Um, well, even though it's busy during this times, I just want to say I really appreciate you guys coming out to the lecture. Even though it's virtual and everything, at least I know from my own experience, whenever there were recorded lectures like this, sometimes only like 3 or 4 students would come to the lecture, and so the fact that so many of you guys are still coming out despite the fact that these are recorded, it means a lot. And I just want to say I appreciate it, because it's talking to your computer screen is one thing, but talking to a computer screen when there's at least 25 people in the room is slightly better. So just want to say thank you guys for that. Okay, and so today the plan is to mostly start a new set of lecture notes. But there is one last thing I want to cover from convection, just because I know at the end of the last lecture, everyone was kind of, mostly fixing their code. And so I do want to cover cross-stream diffusion again, just to make sure, that, we understand that well. Because that is, I'm not saying that it will be, but it's possible that cross-stream diffusion will be on the midterm a week from now. Okay. And so with that, there's also our midterm is going to be next Wednesday. And so make sure you vote in the poll if you haven't already yet. So what I'm going to do on Friday is I'm going to record a review video to basically help you guys review for the midterm. And the way, and just to kind of say it again, for those for those midterm reviews, what I like to do is instead of kind of just going just very lightly over everything that we covered, because we've covered a lot up to this point. I'd rather spend the time and really go into detail on the subjects that people feel most uncomfortable with. And so if you vote on the topics that you feel most uncomfortable with, that really helps me inform what to cover in the review session and really make it useful for as many people as possible. Okay. And so I think I sent out the link for the poll in an email earlier this week, but you can also access it from Canvas on the quizzes page. Okay. Um, and since we're a week out from the midterm, I just want to also remind you of the study guide. And so definitely take a look at the study guide that's posted on Canvas as well. And that'll help make your studying a lot more efficient, because we've covered a lot of lecture notes up to this point. And when you're studying for the exam, one way to study is to just simply read all the lecture notes. But I think that's I think there's better uses for your time, because there's a lot of lecture notes out there. So use the study guide. Use that to help you guide your studying. So what I would recommend is, have the study guide open and then go learning objective by learning objective, and then see if you can know those learning objectives, and see if you can answer those questions. If not, then go into the lecture notes and find the solutions for those learning objectives from there. But don't just read the lecture notes kind of front to back, because that's I think that's kind of an inefficient use of your time, and you tend to not retain all that much. Okay. All right, and so there's also homework 3, and so homework 3 was posted on Tuesday, and that's going to be due on Monday. Okay, and so that's I know that there's kind of a short turnaround time for that, but I wanted to make sure you guys get some practice with convection before the midterm. And usually what I do is I don't post the homework solutions until after I grade them. But since homework 3 is going to be due kind of right before the midterm, I'll post the solutions to that right after it's due. And so by 12:01 a.m. on Tuesday, next Tuesday, you'll have the solutions for homework 3, so that you can have them to study for the exam as well. Okay. Yeah, so the study guide's already up, and so if you look into the file section, I think it's in the lecture notes folder for the files on Canvas. You'll find it there. I think I also sent it out in an email too, and so definitely check the previous emails from this class. And the homework solutions are also up as well. And so I think right now only homework 1 solutions are up. I'm working on grading homework 2 right now, so I should have homework 2 graded by tomorrow. And as soon as I finish grading that, then I'll put homework 2 solutions up as well for that. Okay. And so there any questions on just anything that I've covered so far before we get started? Okay. All right, so let's go ahead and jump right into it. Okay. And so I do want to cover one last thing. So I know on Monday what I said was, Monday was kind of the cutoff for the first midterm, but we didn't really get to cover this last part in good detail. So I want to make sure I explain it and just to kind of make sure that it's good. Okay. And so the last thing that we covered on Monday's lecture was this idea of cross-stream diffusion. Oh, sure. Mm-hmm. Okay. You good? Great. Okay. And so what we were covering was cross-stream diffusion. Right? And it's this idea that whenever you solve a convection diffusion equation in 2D, what can happen sometimes is you have an artificially enhanced diffusion constant. Okay. And so the key word here is artificially. And so this isn't real diffusion. It's kind of just a product of the numerics. And so just kind of just based purely on the method that we're using, the diffusion kind of ends up being higher than it actually is. Okay. And so to quantify this, I called it K false, right? And I gave it the symbol K because that refers to, back to our original convection diffusion equation, right? And so if you think back to our original convection diffusion equation, it looked like this, right? Okay. And so here's our original convection diffusion equation. And then you can see that we have this parameter K right here. Okay. And this parameter K, remember, that was our diffusion coefficient. And the diffusion coefficient basically tells you how strong diffusion is in that, in this problem. Okay. And so what can happen sometimes, or what happens all the time when you add convection onto a 2D situation, is that this diffusion constant gets enhanced, right? And so it's no longer just K, it becomes K plus K false. Okay. And this K false here is erroneous, right? So it's we don't want it there because it's it's first of all, it's artificial, okay, and it's usually not good. Right? And if you remember, the reason we have this false diffusion, or the reason it comes about, is the fact that this happens when our convection velocities are not aligned with our grid. Okay. And so what I mean by that is basically a situation like this, right? And so in 2D, remember we have our waffle pattern, right? Okay. And so our grid looks something like this. So we have basically vertical lines and horizontal lines, and they're all like that. When you add convection to this, the convection velocity can go in any direction that it wants, right? And so kind of in the worst case, you might have a convection velocity that looks like this, where the direction is not aligned with the grid at all. Okay. And at worst, what can happen is this convection velocity can be, basically at a 45-degree angle. Okay. Where this is the angle theta that I'm talking about right here. Okay. Right. And so, theta equal to 45 is the worst case, because that's where it's kind of farthest away from either the horizontal grid lines or the vertical grid lines. Okay, so it's basically kind of right in the middle. Right? And so K false is maximized basically whenever you have this angle is 45 degrees. And what that does is it creates kind of this artificial diffusion. Okay. And so, I don't want to write out the equation for K false again, because it's kind of long, and you don't know, no one actually uses that anyway. But what I want to highlight to you guys is the fact that this artificial diffusion or cross stream diffusion is worse when the angle is 45 degrees. Okay. And so there's a number of ways that we can fix this, and we unfortunately, I'll save that for much later in the class, because it's a little bit of an advanced topic, but in a nutshell, basically the way that we fix this cross stream diffusion is that we change the way that we discretize these convection terms. Okay. Because right now, if you remember, the convection terms, we're discretizing them with just a basic, just either a central difference or backward difference. But there are other higher order schemes out there that are more accurate, that can get rid of these, that can eliminate this cross stream diffusion. But once you start getting into those higher order schemes, that's when things start to get really really messy, and you start to involve a lot of terms there. All right, let's see. So is there a K-false version of kinematic viscosity or something analogous to it? Yeah, so actually in CFD codes, K-false will essentially be, an artificial viscosity. And so that's kind of the term that they use for that. So right now we're doing kind of just a general conservation equation. So I'm calling it just the diffusion constant. But when you're talking about fluid mechanics, viscosity is your diffusion constant. And so when you have this kind of misaligned grid, you can have basically an artificial viscosity. Most commercial codes kind of deal with this. And so a lot of times, like if you're going to be using ANSYS or OpenFOAM or something like that, they'll deal with it, because, obviously, a lot of people know that this is kind of a big issue. But if you're developing your own code, you need to be kind of aware of this, and kind of deal with it, or at least at least know that it's a thing. Okay. So this part of today's lecture will be on, it might be on the exam. I'm not making any promises, but this is part of the convection lecture. So this is basically what we're supposed to cover at the end of the lecture on Monday. But I know everyone was kind of trying to fix their code at the same time, and so I just wanted to make sure that I covered again, just to make sure that we everyone kind of gets a good exposure to this. Well, I mean, that's assuming that we finish this on Monday. So when I started the lecture on Monday, I didn't know that I wasn't going to finish this. But this is just a conceptual thing. So it's this isn't anything that you would implement in the code or anything like that. This is it though. Once I turn this page, then this is it for the first midterm. That I can promise for sure. Yeah. Okay. So any questions on cross stream diffusion? Okay, so now let's officially turn the page on this, and let's close lecture note 06. And so now we're going to start the next set of lecture notes, which is 07. And so starting from here, 5:44 p.m. on Wednesday, March 3rd, none of this is going to be on the first midterm, right? That I can promise you. Okay, and so we're starting a new set of lecture notes now, and basically a new set of techniques. And these techniques have to do with unsteady problems. And so the title for these lecture notes is Time Marching Schemes for Unsteady Problems. Okay. And so now we're going to start to introduce unsteadiness into our, into our equations. Okay, because up to this point, we've basically covered diffusion, and we've covered convection. And so both of these guys are, I consider these to be kind of the spatial processes. Right? And so what they basically do is they basically describe, how our quantity phi, which remember could be temperature, it could be mass, it could be fluid velocity. So diffusion and convection have to do with how this thing distributes in space. Okay. And if you notice, up to this point, whenever we got a solution, whether that be, an exact solution or a numerical solution, they've only been a function of space, right? And so we've only just basically covered phi of x in the 1D case. Right? And in the 2D case, we've been covering, phi of x and y, right? And so both x and y, these are spatial coordinates here. And so, we've only been considering space, okay? But that kind of prevents us from analyzing a lot of really interesting engineering situations, because a lot of engineering situations are not just steady state. Okay, because a lot of times we're going to have to deal with situations that vary with time. Okay. Okay. And so in order to tackle these kinds of situations, we're going to need a new set of theory. Okay. And so some examples of situations that vary with time could be, maybe you're modeling the temperature of a roast chicken that's baking in your oven, right? And so as time goes on and as the chicken sits in the oven, then the temperature of that chicken is going to go up over time, right? And so that's not really a spatial process, but that's more of a time-dependent process. Another example, maybe in kind of a more engineering sense, maybe you're modeling the airflow on an airplane as it takes off from the ground, right? And so as the altitude of the airplane kind of goes up, and as it leaves the ground and it levels off, the airflow around that airplane is going to change with time. Okay. And so right now we're not equipped to deal with these things because we can only deal with just steady state situations. And so in order to deal with unsteadiness, we basically need a new set of techniques. Okay. And we also need to add to our governing equation. Right? And so let me write out the 1D version of the conservation equation, at least what we've been working with so far. Okay. Okay. And so here's the 1D version of the conservation equation that we've been working with. And so first we have the convection term. Next we have diffusion. And then finally we have our source, right? Right. And so, at this point, we can solve this and we know how to solve these guys in 1D, okay? But in order to tackle unsteady problems, we need to add the final member of this team right here. Okay, and that's the term with the time derivative. Okay, and so this term, because it has a derivative with time, we call this the unsteady term. And if you look back to our review of fluids and heat transfer, you can see that now that we've added the unsteady term, we've basically added all the terms that we want to consider in this equation. So at this point, we can kind of say that the gang's all here. And so now we're ready to solve kind of the full shebang, or the full equation. Okay. Yeah, that's right. That's a good analogy. So now we're assembling the Infinity Stone. So now we have everything, and we're ready to snap. Okay. And so basically the subject for the lecture today and Monday are techniques to basically for discretizing this term. And the reason I leave this one off on the first midterm is because these techniques are going to be very different compared to what we have been doing. And so we're still going to be doing finite differences, but the way that we apply the finite difference is going to be pretty different in here. Okay. And through this, we're able to hatch a whole new class of schemes called time marching schemes. Okay. All right. Any questions on this before we move on? Okay. All right. And so just to kind of repeat kind of what I just said, this class of techniques in order to solve an unsteady problem, these are called time marching schemes. Okay. And the reason it's given this name is because we're literally going to be marching our solution forward in time. Okay. And we're basically going to be solving the solution one time step at a time. Okay. And so programmatically, what this means is, a loop is basically a necessity. And so, anytime we have a time dependent problem, we're going to be using a loop to do that. Okay. All right. And so the other fun thing about unsteady problems and time marching schemes is that it actually changes the way that we view our solutions. Okay. Because up to this point, and you've seen this on homework 2 that you just turned in, and on homework 3, when we run our code, we just get a still image of what the solution looks like, right? And so we either get a curve in 1D or we get kind of a nice color contour in 2D. But now, since our equations here is going to be time dependent, what's going to happen is that now our solutions are not just going to be still images, but they're going to be movies. Okay. Okay. Or in other words, they're going to evolve with time. And the best way that we can view something that evolves with time is with a movie. And so once we start getting into maybe not today, probably on Monday, once we get into a lot of the MATLAB implementation, you'll see the MATLAB code that you need to actually produce a video. And so that part I think is pretty cool, and you can actually see your solutions changing in real time. And part of the from homework 4 onwards, part of your homeworks will be uploading these videos onto Canvas. Okay. Okay. And so that's kind of an introduction to the time marching schemes, or kind of where we're going. And the other thing that we're going to need now is a certain kind of condition, right? And so for spatial problems like diffusion and convection, we had boundary conditions, and boundary conditions were basically conditions on the spatial domain. So we're still going to need boundary conditions, but now that we have this time component here, we're going to need an additional type of condition in order to specify our solution, and that's called an initial condition. Okay. And so what initial conditions are is that these define what the solution looks like at time is equal to 0. Okay. Movies, yes. Yeah, or videos, or animations, GIFs, whatever you want to call them. Okay. And so what you'll see, once we start working on our time marching schemes is that, we always need to start from something. Okay. And so our initial condition, you can almost think of it as giving us a starting point. And so from that starting point, we can then march our solution forward in time. Okay. And so I want you guys to kind of keep that in mind as we solve these problems, because we're going to need that initial condition. Okay. All right. And so unfortunately, since we're introducing kind of a whole new set of theory here, we need some additional notation. So we need some more bookkeeping. All right. And so if you remember, when we started doing our 2D diffusion, we spent a lot of time talking about the IJ notation and the ID numbers, right? And so, this is just kind of a necessary evil whenever you're working with any computational method, is that you always need, some notation or some ways to keep track of stuff. So it's not the most exciting thing, but it's necessary in order to keep our, our solutions organized. Okay. All right. And so if we think about kind of the general case for 2D, we use the IJ notation to denote spatial coordinates. Okay. And so we basically, every node in our grid had an I value and had a J value, and that tells us basically where our nodes were located. Okay. And so for time, time doesn't exist on the same plane as space, and so we're going to need a different notation for this, and for that we're going to use n for this. Okay. And in fact, we're going to put these onto the same phi value or the same phi as the I and j, right? So remember, for I and j, or the spatial location, we put that into the subscript of phi. And so now that we're introducing time, we're going to put time in the superscript. Okay, so you're going to see it's going to look like this. Okay, and so this is what we had previously, right? And so if we wanted to say the phi value at I comma j, we put the I comma j in the subscript here. Okay, so this is the spatial coordinates. Okay. And then to denote time, we're going to use a superscript. Okay. And then we're going to put the superscript up there, right? And so this guy in the superscript here, this is going to be our time index. Right? And so the notation is going to get a little bit messy now, because now we're dealing with two types of indices. And so we have the space on the bottom and we have the time up top. Okay. All right. Any questions on this? Okay. All right. So Juan, your question is: are you asking if it's a parametric equation that we're going to solve for it in T? So I think the solutions are I always never remember whether, like, what's an elliptic equation, what's a parabolic equation, and things like that. Oh, okay, I see. Yeah, I can go back. Okay. All right. And so, now we have this time index n right here. So in particular, I want to define two indices. So, I've defined this time index n, but there's kind of two categories that I want you guys to keep in mind. Okay. And so one will be the solution at time n. the other one that I want you guys to remember is the solution at n+1. Okay. Right. Is this similar to a data logger that measures things at specific time ticks? I would need to kind of think of that for you can kind of almost think of it like that, actually. Yeah. So the solution will basically, we'll be solving our solution at specific intervals at different time ticks, and then in the end we'll kind of build it all together into one solution. Okay. And so when I say that we have the solution at time n, this is time n refers to the current time. And so usually what we assume is that if we have the solution at the current time, this is what's known. Okay. Right. Or in other words, we've already kind of solved for the solution at the current time. Okay. And then the time index n+1, this is the solution at the next time. And these are usually unknown. Okay. Right. And so I know these are kind of very vague terms, but hopefully once we start solving problems, it becomes a bit more clear. Okay. But just to kind of give you a quick explanation here, let's take our initial condition as an example, right? And so our initial example, our initial condition, that's we need to specify what our solution looks like at time 0, right? And so once we specify that, then we can basically say that we know the solution at time equals 0. Okay. And so that basically sets our current time, right? And so the goal for the time marching scheme, or the goal for the numerics, is to solve for the solution at the next time. Okay. Or in other words, we're going to have situations that look like this. Okay. And so what we have on the left-hand side of the equal sign here is, this is going to be the solution at the next time step. Right. And this is what we want to solve for. And so, when we implement our time marching schemes, they're explicitly, designed to solve for, what's the solution at the next time step, right? And the way that we're going to do this is we're going to take the solution at the current time. Okay. And so this right here is the solution at the current time. Okay. And, I'll remind you that, the solution at the current time is known. Okay. Okay. And then what we're going to do is we're going to apply a time marching algorithm to it. Okay. And so it's a bit hard to kind of write an algorithm kind of a simple way like this, but I can basically just call it just like this f, right? So this f is some function where this function is going to be basically our time marching scheme. And so all time marching schemes basically follow this basic principle. So what the time marching scheme will do is it'll take the known solution at the current time, apply some work to it, apply some math to it, just kind of based on the scheme. And then from that, we're able to solve for the solution at the next time step. Okay. And so it's kind of a process where, just like you mentioned before, we're solving for the solution one time step at a time, right? And so we're going to start with the initial condition, which we're going to know. And then from the initial condition, we're going to solve for the solution at the next time step, okay? And then once that solution is known, then we're going to take that solution and then we're going to solve for the next one at the next step, okay? And this progresses until we basically solve for the solution at all the time steps, okay? All right, any questions on this so far? So hopefully this becomes a little bit clearer, because I after we do some examples, because I know it's still a little bit dry right now. Okay. All right, and so let's start implementing some methods. So so in this class, I'm going to stick to mostly just the two simplest methods. And so the two simplest methods are explicit Euler and implicit Euler. But just also know that there's lots of different time marching schemes out there, and there's so many that it's impossible for anyone to know all of them, because typically what's done is that a scientist or an engineer, they work on their code, and then they develop a new scheme and then they name it after themselves. But if everyone does this, then then it's hard to kind of keep track of everything, right? And so what you'll see from a lot of these techniques is that a lot of these are named after certain people, which I personally hate, because it's hard to look at a method like the Crank-Nicholson method and know what it's about, because those are just two dudes' names, and so I have no idea what that thing is about. Okay. All right, but let's start with explicit Euler, because this is kind of the simplest time marching scheme out there, and it's kind of the first one that everyone learns. Yeah. And so explicit Euler, basically what we're going to do is we're going to apply a forward difference scheme to the time derivative. Honestly, everyone pronounces these differently. So you can call it Euler, you call it Euler. I personally don't know the guy, so I'm not going to get offended by it. But I'm sure he's okay. I'm sure he's okay with any pronunciation. I say GIF. I think GIF is even though I know the guy that created it calls it GIF. I refuse to call it that. Oh, really? Okay. Well, I personally don't care for it. Okay. All right. And so explicit Euler. So this is the simplest one, and we're basically going to apply a forward difference to the time derivative. Okay. 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 So let's start with our conservation equation. But I'm going to move the convection term to the right-hand side, just so that we can isolate the unsteady term, right? And so our conservation equation looked like this, at least in 1D. And so we had our unsteady equation, our unsteady term here. And then we had our convection term. So we had minus u d phi dx plus k d squared phi dx squared plus q of x. Okay. All right. And so just like we've always done with these equations, let's apply a finite difference schemes to all the derivatives. Okay. And so, I know we have the convection term here, and I know, there's a lot of things that we can pick for this. But for now, I'm just gonna keep it as central difference, just to kind of, keep it simple. Okay. All right. So actually, I'm gonna do the right side of the equal sign first, because we've done all these before. Right? All right. So first we have the convection term, and so this is gonna be a minus u divided by 2 delta x, right, times phi plus 1 minus phi minus 1, okay, plus k divided by delta x squared times phi I minus 1 minus 2 phi I plus phi I plus 1. Okay. And then we have our q I here. Okay. Let me fix the q so it looks different. Okay. And so all that we've done before. So that's basically just applying, our central difference schemes to our spatial derivatives. And so now let's apply our forward difference scheme to the time derivative. Okay. And so remember, forward difference scheme, we have phi minus phi. Okay. And then we're going to divide by the spacing. But now since we're working with time, we're going to divide by delta t instead of delta x, where delta t here is just going to be our time step size. Okay. Right. And instead of derivatives in space where we apply the changes to I, since we're performing this derivative in t, we're going to apply those changes to the time index. Okay, and so instead of I plus 1 and I, we have n plus 1 and n. Okay.
Professor, the minus 2 phi on the right plus, is that a plus on the bottom?
Yeah, it's a I
Okay.
plus, yeah, phi I plus 1. That's the last one.
Okay, thank you.
Okay. And so that's all the finite differences that we're applying here, but we're not done yet. And so if you'll notice, the phis on the left-hand side, they only have a time index, and then the phis on the right, they only have a space index. And so we need to label all of our phis here with both a time and a space index, right? And so let's go ahead and fill in all the indices that are missing, okay? And so for all the phis that are missing a space index, okay, I'm going to apply a space index of just I, okay? And so that's only going to apply on the left-hand side. And so both of these phis, phi I plus 1, or phi n plus 1 and phi n, I'm going to give those a space index of I, okay? And for everything that's missing a time index, I'm going to apply a time index of n, okay? Okay. And so that applies to everything on the right-hand side. And so all of these guys are going to be n right here. Okay. All right. And so now we've labeled the time and space indexes for all the terms here. And so what we need to do is we need to kind of work on this this equation algebraically in order to solve for phi I n plus 1. Okay. And so that's going to be our end goal. Okay. Because if we have an algebraic equation for phi I n plus 1, then that's essentially going to be our time marching scheme. Okay. All right. Any questions on this so far? Okay. And so on the next page, what I'm going to do is I'm going to take this equation here. I'm going to multiply both sides by delta t. And so to kind of get delta t out of this denominator, and then I'm going to add phi I n to both sides. Okay. All right. So let me go ahead and do that. And so if we multiply both sides by delta t and we add phi I n to the other side, we have phi I n plus 1 is equal to phi I n, okay, minus u delta t divided by 2 delta x, okay, times phi I plus 1 n minus phi I minus 1 n plus k delta t divided by delta x squared multiplied by phi I minus 1 to the n minus 2 phi I just by itself raised to the n plus phi I plus 1 to the n, okay, plus q I delta t, okay? All right. And so now we have our scheme that looks like this, okay? And so this is technically the time marching scheme because we've accomplished our goal, and so we've basically isolated phi I n plus 1 over here, but this form isn't that useful because what we typically want is we want to put this in the form where we have just the coefficients for the different phi terms, okay? And so let's rearrange. Okay. In other words, I'm going to combine some terms on the right-hand side to make it so that we have terms for all the different fees. Okay.
I have a quick question.
Yep. What's up?
On the first line, is that u delta t or delta x?
It's u delta t.
Numerator.
Yeah.
Okay. Thank you.
Mm-hmm. Yeah. So that delta t came from the time derivative where we multiply both sides by delta t. Mm-hmm. All right. And so if we go ahead and rearrange the terms, we have this this expression here. Right, so we have u delta t over 2 delta x plus k delta t divided by delta x squared. Okay, and this is the coefficient for phi I minus 1 raised to the n. Okay, plus then we have the coefficient for phi I n, and so it's going to be a 1 minus 2k delta t divided by delta x squared. And this is phi I n plus a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared. And this is phi I plus 1 n. And this is plus our source term, which is q I delta t. Okay. And so it's a lot of terms here, but it's the nice thing about this is that this is basically just a plug and chug for this, okay? And so this equation right here, this is our time marching equation for explicit Euler. And so the way that you're going to use this equation is that you'll see in the next example that once the problem is given to you, you'll be able to plug in the values for k, you can plug in the values for u, for delta t and delta x, and you just get a simple kind of algebraic equation that you can just apply over and over again. Okay, and so it looks intimidating, I know, because it's a lot of different terms, but once you start plugging things in, it becomes pretty easy to work with. All right, any questions on this before we do an example? Okay, maybe you guys maybe 30 more seconds to kind of write this down because I know it's kind of a lot to write down. Okay, so let's do an example. So we're going to start with kind of a pretty simple example, and we're going to consider the unsteady diffusion equation. All right, so no convection for now. So just diffusion and unsteadiness. And so for that, we have d phi dt is equal to 3 d squared phi dx squared. Okay. And so you can see from here that we have a diffusion coefficient of 3 because that's the coefficient out in front of this term. Okay. And then so, before we actually solve this, we need our boundary conditions. Okay. And so on the left-hand side, at x is equal to 0, okay, and this boundary condition is going to be valid at all times. We're going to say that our phi value here is going to equal to 1. Okay, so that's phi at x is equal to 0, comma t is equal to 1. Okay. And on the right-hand side, we have a Neumann condition. Okay, so we have d phi dt, or dx, I'm sorry, d phi dx at x is equal to 1, comma t. And so again, this boundary condition is going to be valid at all times. This is going to be equal to 2. Okay. Okay. And just like I mentioned earlier, so since we're doing an unsteady problem here, we also need an initial condition that defines what our solution looks like at t is equal to 0. Okay. Okay. And in this case, we're going to assume that the solution is going to start out at 0. Okay. Right. And so we start with basically a 0 initial condition. So this is fairly common just because mathematically this is really simple to do. So you just use a zeros function in MATLAB. Okay. Okay. And so before we end up solving this, because I know probably some of you guys have probably noticed this, is that we have a little bit of a discrepancy between our boundary conditions and our initial condition, right? Because if our initial condition says that everything starts at 0, how could this be consistent with our boundary condition here, which says that phi at x is equal to 0 is equal to 1, right? And so we have an inconsistency. And so, for this, I will say that, it's usually okay for this. So a lot of times your initial conditions won't be consistent with your boundary conditions at the first time step. Okay. But that's okay, because what's going to happen is that, for that first time step, we have that discrepancy, but as soon as we start time marching, then the boundary conditions will be satisfied. Yeah, you'll see. So you'll see, how we apply the explicit Euler. And so once we start implementing it, it'll start to become pretty clear. Okay. All right. And so, in order to solve this, we also need to specify values for our time step size and our grid size. Okay. Okay. And so for the time step size, let's use a time step size of 0.1 seconds. Okay. And so this tells us that, when we're solving our solutions, each solution that we solve is going to be separated by, 0.1 seconds in time. And then we also need to specify our grid size. Okay. And for this problem, let's assume that we have a grid of 5 points. And so delta x is going to be 0.25. Okay. And if we want to put units on this, we'll call it meters. Okay. Okay. And so here we have, our first kind of unsteady problem here. And then what we're going to do is we're going to apply the explicit Euler to march this forward in time. Okay. All right, and so to do this, all we're going to do is we're going to take our equation that we had on the previous page, okay, and just start plugging in values for k, delta t, delta x, and u, okay, and q, I guess, but there's no q in this case. Okay. Because what we have here is we have everything that we need. So we have k, we have delta t, we have delta x. It's not given here, but we also have u. Okay. In this case, u is equal to 0, so we have no convection velocity, and so we can just kind of plug all that stuff in. Okay. And so if we plug all these values in, so we plug k is equal to 3, u is equal to 0, delta t and delta x, we get the following equation. And so remember, for a time marching scheme, we're gonna always have an equation for phi I at n+1, okay? Right? And so we're gonna start with the phi I minus 1 term, and so the coefficient is gonna be 4.8, and then we have a coefficient of 8.6, and this is in front of phi I n, okay? And then we have another coefficient of 4.8 of phi I plus 1 n. Okay. Right? And so there is our time marching scheme. But this isn't the solution here. And so what we're going to do from here is we're going to apply this time marching scheme to every value of I in our grid. And in this particular case, since we have 5 grid points, we're going to apply this for I is equal to 1, 2, 3, 4, and 5. Okay. All right, any questions on this so far? Yes. Right. So the way that we got this was we basically plugged in all these quantities here. So we have k, we have u, we have delta t, and we have delta x, and then we plug those into this equation on this side over here. Yep. Or you're getting 9.6. Let me see. And so let me see. So we have 1 minus 2 times 3 times 0.25 divided by divided times 0.10 divided by 0.25 times 0.25. I got minus 8.6. Did you do the 1 minus? Yes, you need the 1 minus there. Mm-hmm. Yep. Mm-hmm. Okay. And so let's see how we actually apply this in practice. All right, and so let's take this equation and just like we do for the steady state cases, let's apply this at every node in our grid. And in this case, since this is just kind of a worked out problem, our I values are going to go between 1 and 5. Okay. All right, and so we're going to have an equation for I is equal to 1, equation for I is equal to 2, equation for I is equal to 3, I is equal to 4, and I is equal to 5. Okay. Okay. And so since we know that I is equal to 1 and I is equal to 5 are boundary conditions, I'm going to save those for last, right? And so let's apply this equation here to all of our interior nodes. And so that's going to be nodes 2, 3, and 4. Okay. Okay. And so when we apply it to when I is equal to 2, what we have is phi 2 at n plus 1 is equal to 4.8 phi 1 at n minus 8.6 phi 2 at n plus 4.8 phi 3 n. Okay. Right. So we're going to have a similar equation for phi 3. Right. So it's phi 3 n plus 1 is equal to 4.8 phi 2 n minus 8.6 phi3 at n plus 4.8 phi4 at n. Okay. Right. And then for the last interior node, we're going to have phi4 at n plus 1 is equal to 4.8 phi3 n minus 8.6 phi4 n plus 4.8 phi5 at n. Okay. Okay. And so those are all the interior nodes. And so this is, very similar to what we've done in the past. And so, once we got our finite difference equation, we just applied it at every interior node that we can. Okay. All right, so let's talk about the boundary conditions. And so if you remember from the previous page, we have our boundary conditions. We have a Dirichlet boundary condition at x is equal to 0. Okay. And so that Dirichlet boundary condition basically says that phi 1 is equal to 1 at all times. Okay. And so basically what we can say is that phi 1 at n plus 1 is going to be equal to 1. Okay. Right. And so because this Dirichlet boundary condition is valid at all times, it's also going to be valid at the next time. And so that helps us out right there. Okay. Okay. And so now let's talk about the Neumann boundary condition. Right. So the Neumann boundary condition looks like this. Okay. And so we had d phi dx at x is equal to 1 and t is equal to 2. Okay. And so just like before, we're going to apply a finite difference scheme to this. And so if we apply a finite difference scheme to this derivative, we're going to have phi. In this case, since we're doing this for x equal to 1, this can be phi 5 minus phi 4 divided by delta x, and this is equal to 2. Okay. Okay. And so at this point, we need to kind of formulate this equation in order to get an expression for phi 5 n plus 1, right? Because that's ultimately what we want in this set of equations right here. Okay. And so we want an equation for phi 5 n plus 1. And so in order to get that, we're going to take this finite difference derivative, which we have on the bottom here, and then we're going to apply a time index of n plus 1 to phi 5. Okay. And then on phi 4, just so that we can form an equation for it, we're going to apply a time index of n. Okay. And this is, I would say this is kind of fairly arbitrary here, but this is all just for the sake of getting an equation for phi 5. Okay. And so if we solve this equation for phi 5 n, then we get phi 5 n plus 1 is equal to 2 delta x plus phi 4 n. Okay. And for this particular problem, since delta x is 0.25, what we get is 0.5 plus phi 4 n. Okay. All right. And so with that, we have our 5 equations that we're going to need that we can use to advance this system forward in time. Okay. All right. Any questions on how we got these 5 equations here? Okay. All right. And so now that we have these equations in this form, we're ready to time advance. But just to kind of make the computations more convenient, just like we've done for the steady state cases, let's take the set of equations and put it into a matrix form. Okay. because we know that MATLAB and Python and all those other programming languages, they work great with matrices. And so if we can formulate our problem with matrices, then then that's going to be easy to program. Okay. And so the matrix form looks like the following, right? So first we're going to have all the phi terms, all the phi n plus 1 terms here, okay? And so we're going to have phi 1 through 5, and all this is going to be evaluated at n plus 1. Okay. This is going to be equal to the following matrix, which is going to be multiplied by phi at n. Okay, so let me go ahead and fill this in first, and then you'll see, where this basically came from. Okay. Right, so there's our coefficient matrix, and then to this we're going to add, or we're going to multiply by the phi values at time is equal to n, right? Right, and so that's phi 1 through 5, but this is going to be evaluated at n, okay? And then to this we're going to add those extra terms, okay? And so if you look at kind of our equations that we had on the previous page, we had some terms primarily from the boundary conditions that that wasn't multiplied by phi. And so in order to account for that, we can just simply add a vector here. Okay. And so this right here, this is the matrix form for our explicit Euler time advancement. Okay. Okay. And so now we can actually start using this to solve. Okay. And so remember what I said about the n indices, right? And so whenever we have an index of a time index of n, this is something that's known, right? And so everything that's on the right side of the equal sign here, all these things should be known. Okay. And so, the way that you actually start to use this for time marching is you start with the initial conditions, okay? Okay. And where you're going to plug the initial conditions are in is right here, okay? And so the very first phi n, the first known time step, you're going to plug in the initial conditions for that, okay? And so after you plug in the initial conditions, remember our initial conditions, we assume everything is 0, right? And so let me go ahead and plug that in. And in fact, once we start plugging in the initial conditions, that's going to be n is equal to 0, right? Right. And so the very first, solution that we're going to solve for is for n is equal to 1, or for the first time step, right? And so the time index for this first solution that we're going to solve for is 1. And so we have phi 1, 2, 3, 4, 5, and the time index is 1. So let me go ahead and fill in this matrix again. And instead of, phi 1, 2, 3, 4, 5 at n, we're plugging in our initial condition, which is just zeros all around. Okay. And of course, we have our added terms on this side right here. Okay. And then to actually solve this system, all we have to do is just perform the matrix multiplication. Okay. And so this is kind of a hallmark for explicit Euler. So explicit Euler, is very nice in the fact that you don't have to perform any solving of a linear system of equations. All you have to do is just perform some matrix multiplication, which relatively speaking is a lot faster than doing the backslash or doing any kind of matrix solve. Okay. All right. And so once we do that, we'll have the solution for the first time step. All right. Any questions on this so far? Okay. All right. And so by performing these multiplications, we can see we start from all zeros. We can see that this entire term is just going to go away because we perform matrix multiplication by zeros. Okay. And so, after we do that, then what we get is phi 1, 2, 3, 4, and 5 at the first time step is equal to 1, 0, 0, 0, 0.5. Okay. Okay. All right, so that's great. And so from here, we're not done yet because now we're going to take this solution and then use that solution to solve for the solution at the second time step. Okay, and so let me go ahead and write out the system again. Okay, so this can be phi 1, phi 2, phi 3, phi 4, phi 5. Okay. And now we're solving this at the second time step, right? So this is going to be time step 2. Okay. You'll see on this next step, we're not going to cancel the big matrix. We're actually going to multiply it through, right? And so we have 0, 4.8, 0, 0, 0, 0 minus 8.6, 4.8, 0, 0, 0, 4.8, minus 8.6, 4.8, 0, 0, 0, 4.8, minus 8.6, 1, 0, 0, 0, 4.8, and 0. Okay. But now, now that we're on the second time step, we're going to plug this guy into phi n right here, right? And so now this is going to be 1, 0, 0, 0, 0.5. Okay. And to this, we're going to add, boundary condition term again. Okay. And so when you solve for this, we're going to get phi. We're going to get all the phi values at time step 2. Okay. And so this time it's not going to cancel out because we have, ones and, 0.5 there. And so when you perform the matrix multiplication, what you get is 1, 4.8, 0, 2.4, and then 0.5. Okay. And so this is phi I at the second time step. Okay. Let me do n is equal to 2 right here just to kind of specify that. Okay. All right. And so from here, what you can do is you can just basically, repeat this process where like now that you have phi at n is equal to 2, you plug this back into the system and you can solve for phi at n is equal to 3. And you solve this, over and over and over again until you reach, the end, right? And so usually for these kinds of problems, you kind of specify ahead of time how many time steps that you want to solve for. And so if you want to solve this for 5 time steps, you're going to repeat this process, 5 different times. Right? And so, you probably see that, doing these problems by hand gets really tedious after a while. And so, that's why we do these kind of computations in a loop. Okay. All right. And so we're out of time for today. So, I'll show you, the implementation of this in MATLAB on Monday. And then we'll finish that up, and then we'll learn about implicit Euler. Okay. All right. So thank you guys for tuning in today. Remember to vote in the midterm review poll if you haven't already. Have a great weekend, and I'll see you on Monday. Thanks, guys.
So I had a question.
Sure.
A second.
Professor, I had a question too.
Sure. Yeah, what's up?
For homework number 3, I was reading the problem for the two-dimensional.
Yep.
It mentioned not to use the central final difference equation for the convection. Does
Yep.
that mean do we use the forward or backwards to solve for it?
Yeah, so it depends. And so it depends on whether the convection velocities are positive or negative. And so if the convection velocities are positive, then I want you to use backward difference for that. But if the
Okay.
convection velocities are negative, then you should use forward difference for it. Yeah.
Oh, okay. Thank you. I got stuck in that part.
Oh, yeah.
All right. Thank you.
Yep. Thanks, Sasha.